Hello and welcome to the latest NXP quick learning about our power MOSFET devices. My name is Chris Boyce and I'm one of the power MOSFET team based here in Manchester in the UK. Hopefully you've seen some of our other power MOSFET quick learning videos where we've explored our devices and some of their characteristics in detail. Today I thought we'd do something a little bit different and have a little quiz and discuss maybe some 10 miscellaneous MOSFET facts. So we can kick off straight away and go through these. So we start at number 1 here, when we talk about when was the first MOSFET structure patented. I'll give you a moment or two to think about that as we go through. Well, the answer is the first MOSFET structure was patented way back in 1925. So it's a long time ago since that device was first conceived of and first protected, and now they're in use in their hundreds of millions and billions across the world. Secondly, interesting fact here, the MOSFET is the most common humanly fabricated device in the history of the world. We as a species have made more MOSFETs than we've made of anything else. And the reason that we can say that with some certainty is because MOSFET technology is used in the very latest and greatest VLSI technology, integrated circuits, where very many devices are crammed onto a piece of silicon that goes to control all of the sorts of devices that use microprocessors and similar devices. So just to take a comparison here, if we talk about a MOSFET inside an integrated circuit, this is the sort of device you might find inside an Xbox One that's doing all that clever processing to make your games look so realistic. So the system on chip that sits inside an Xbox One, it has a piece of silicon of the area of about 363 millimeters squared, and crammed onto that single piece of silicon there are, anybody know? The answer is something like 5 billion transistors. 5 billion transistors on that single piece of silicon. The devices that we're more interested in talking about today, however, are what we call power MOSFETs, and these are on a much larger device. So if we look at the NXP D2 pack as an example, where you might have a piece of silicon inside a D2 pack that's maybe 30 millimeters square, 30 square millimeters, and in there we've just got a single transistor, so clearly a huge difference in terms of scale. But the reason for this is because whereas here we're moving very tiny amounts of charge around to create our ones and zeros to get our digital processing working, here we're having to switch very large currents. So I mean, here we're talking about currents that are switching somewhere in excess of 100 amps. And that obviously has its own power limitations, and therefore we can't cram the devices so closely together, because we've got to make sure that we can that the devices don't get too hot and don't operate correctly. Okay, so question number 3. Somebody patented superjunction MOSFET technology back in 1984. Well, you've tuned into an NXP quick learning video, so I guess you would only expect us to say that in fact it was our very good selves, NXP, who patented that technology, although it was at a time when we were known as Philips Semiconductors rather than NXP. We've had a name change since then, but that stems back to our research scientists at the time. As we've come down to number 4, what's the sort of best-in-class performance we can get in terms of RDS on, so the on resistance of the device, for a 30 volt Power SO8 compatible package, something that's 5 millimeters by 6 millimeters? Well, we're now down to a point when that device is fully turned on, we're down in the area of about 1 milliohm, okay? And that means that a thousandth of an ohm in our conduction losses inside our switch mode power supplies and other devices. We can clearly get the on resistance and the I squared R losses, the conduction losses associated with that power supply, down very low, because we, amongst other manufacturers, have managed to squeeze the on resistance down to that sort of level. Having got the conduction losses down, the next challenge in the sort of switch mode power supply arena is to try and make the devices switch as fast as possible, because it's the transition between the on and the off state and the on and the on state where the most power is dissipated. When they're fully off, then obviously the current is approximately zero, so the power dissipation is approximately zero. And when they're fully turned on, with such a low on resistance, then we have again a very low I squared R loss. So if we can squeeze the time it takes to switch the device on and off, we can end up with that much more efficient system. So again, the latest power MOSFETs available from us and others are able to switch in the order of something like 10 nanoseconds. And to put that in context, that's about that's the amount of time that it takes to light to travel just something like 3 meters. So obviously switching very, very, very fast. And that's great in terms of reducing the switching losses inside our power supplies, but it's not so good in terms of keeping our voltage spiking and EMI issues under control. The faster we switch, the more difficult it is to keep that switching under control and make sure that we don't suffer from overshoot and coupling back to the gate and sporadic turn on, etc. We've addressed that at NXP with our latest NextPower S3 range. The S3 stands for super fast switching with soft recovery, a bit of a tongue twister. And we've done this by producing a MOSFET that's capable of delivering very high efficiency, very fast switching, but keeps the spiking under control using our Schottky Plus technology. And the advantage of Schottky Plus, it gives you all the benefits of having an integrated Schottky device, but with much, much lower leakage current. And in actual fact, we've got a little box to fill in here. Our leakage current compared to devices with an integrated Schottky device is something like 1,000 times less leakage current on our device. And that's obviously, again, helps with the efficiency, helps with any battery powered devices to make sure the battery life stays as long as possible. And it also helps us in our manufacturing process, because we use leakage current to determine whether a device is good or bad. And if we have a very high leakage current from the integrated Schottky, then that inhibits our ability to use that leakage current test in our manufacturing plant as a way to weed out the defective devices. Where we have a very low leakage current, we can still use that test, and what it means is that we can identify the defective devices. Number 7, we haven't got a box to fill in here. I just want to make the point, this is a sort of, you sometimes hear people say this. If you look in some older textbooks about MOSFET technology, you'll hear about the parasitic NPN transistors that under certain conditions can turn on and cause the MOSFET to go out of control and fall over into latch up. Well, the good news is in today's technology, we can safely scribble all of that out. We don't really care too much about that, because MOSFET technology, low voltage MOSFET technology today is capable of, or it's been designed in such a way that parasitic NPN transistor has been designed out. So it's no longer something you have to worry about as a designer. Moving on, number 8. So a large amount of our business here at NXP in the MOSFET business ends up with devices going into automotive applications. And if we go back to 1980, the average car had approximately 0 MOSFETs. You might have found the odd one or two occasionally, but generally 0. Today, we're much more likely to find something in the order of 100 to 200 MOSFET devices in each car. Each average size car. They're used everything from small motor control applications such as electronic wing mirrors or moving your seat backwards and forwards, right up to the heavy duty stuff like power assisted steering, anti-lock braking systems. Even your airbag is triggered by a MOSFET. So there's lots and lots of devices that go into the average car today. If we lined up all of the NXP MOSFETs sold last year, how far would it stretch? It would stretch from Manchester to, well, I'll tell you, it goes all the way to Shanghai. That's something like 5,000 or 6,000 miles, 10,000 kilometers. And if you put all of the devices that we manufacture in a year and put them end to end, that's the sort of distance that you would find. And that clearly gives you an indication of just how widely used MOSFETs are in today's life. And finally, we're reaching a point now where silicon is reaching about the end of its performance curve. We can squeeze a little bit more out here and there, but we're really looking to next generation technologies to give us that leap in performance. So there's lots of investigation and research and other activities going on around the new 3-5 materials, such as, in particular, gallium nitride. So we're very active in that area. And there's also the whole idea of silicon carbide, which is being used by some people, which is opening up new performance opportunities within the MOSFET arena. So I hope you enjoyed our little quiz. Thank you very much for joining us. If you'd like to learn more about NXP MOSFETs, please take a look online at www.nxp.com/MOSFETs. My name's Chris Boyce. Thank you very much for listening. Bye-bye.